Hey everyone, thank you for joining us today for our special live stream with Intel. I am so excited about the discussion today. Joining me is Andres Rodriguez, and Andres is a senior principal engineer at Intel. Andres, it's great to have you here.
Thank you. It's great to be here. I appreciate the invitation.
I'm so interested in talking with you. We were just chatting beforehand, and you're the author of a book called Deep Learning Systems. Deep Learning Systems, Algorithms, Compilers, and Processors for Large-Scale Production. And the book describes deep learning systems, the algorithms, and all those things you really need to train and deploy deep learning models at scale and production. And one thing that I was just looking at in the introduction was how quickly we are seeing the number of computations required to train and deploy state-of-the-art models, and how it doubles every 3 to 4 months. And that computation requires at least a fourth order polynomial with respect to the accuracy, and by some tasks as a ninth order polynomial. Now, this is getting pretty deep into what deep learning is, but what does that mean? Every 3 to 4 months? I mean, that is really, really quick.
Yes, thanks for pointing that out. I think it's very important to realize that deep learning started as in the research community with smaller problems and is transitioning to industry, and the set of problems that is tackling are growing both in the size of the deep learning models and the data sets that they're using. And what this means is that one single compute unit, like one single CPU or one single GPU or one single accelerator, is insufficient to keep up with the rapid growth that deep learning models are demonstrating. And so you need a complete system design where you need to take into account not just the compute unit, but also the bandwidth transferring data from memory into the compute unit, which actually it's becoming a bigger bottleneck than the actual compute, and also interconnecting between different nodes. So you need high-speed interconnects, and you need a platform that is balanced, that it can do feed the data, that it can do multi-node training, that it can have high compute for the areas of the deep learning models that are very compute intensive, and also that can do fast single computations for the areas that cannot be parallelized. So designing these deep learning systems is it's an area, fascinating area, that I hadn't seen a lot of documentation on this particular topic. There is a lot of books and documentations and blogs that focus on some algorithms. There is some blogs that focus on hardware, but I saw that there was a lack of a connectivity between the hardware and the algorithms and the software, and that's what the book attempts to do.
You know, I want to just remind everyone who's out there that you can ask questions, that you are free to ask those questions in the YouTube comments. And we really, like to hear it, even more than comments, if you have any observations that you'd like to make. Now, again, in the introduction, you talk about, you talk about these bottlenecks, and you talk about how the evolution of computational growth is really driving innovations in deep learning in those architectures themselves. And you talked about the issues such as memory constraints. And I imagine there's lots of bandwidth constraints too. I mean, we're talking about just massive amounts of data. Our focus was going to be a little bit on deep learning, these deep learning frameworks, these AI frameworks. How is that massive acceleration affecting the frameworks themselves, and what are you seeing happening to the frameworks and how they're being used?
Yeah, this is a good question. The frameworks or libraries are an entry point for data scientists to develop new deep learning models and to run them on deep learning on hardware. And so the frameworks hide a lot of the complexities, both algorithmic complexity as well as mapping the computations to the hardware. And the frameworks have evolved over the past 10 years quite significantly. So 10 years ago, you didn't really have any commercial framework. There was a popular academic framework called Theano, and later the first framework that became commercial was called Caffe. But Caffe lacked a lot of flexibility. So it was very easy to use, particularly for computer vision applications. But outside of those applications, it was challenging. But that was okay because at the time around 2014, computer vision was where deep learning was taking off. But in the following years, deep learning models started to show very promising results for natural language processing, such as translating from one written language to another language, and later doing speech recognition, and even now doing speech generation. And so you needed frameworks that were more flexible. And after Caffe, there's been a number of frameworks that came into the ecosystem, but primarily two have really stood out: TensorFlow and PyTorch. And their most recent versions, they share a number of similarities, and they provide both speed and flexibility, especially for a CPU and GPU. And as many hardware vendors are developing new hardware, then they are working with these two frameworks to make sure that those frameworks can run well on the hardware that they are developing.
Mm-hmm. That hardware that they're developing is also playing catch up, isn't it? It just leaves me thinking, we've all grown up on x86 architectures and how they've been used for distributed computing and how they're evolving. But now what we're finding is distributed architectures are ever more distributed, where now the node might be anywhere, right? That's still something that's, I think, a little bit ways off from people being able to actually harness and use. But how does that play into it? These edge devices, this capability to use nodes, and how does that affect the hardware itself?
So you have primarily two types of hardware. One is the traditional x86 that is very good for a broad set of workloads. And as deep learning requires a lot more compute, a number of other hardware is being used in the data center. So I'll get to the edge in a minute. So in the data center, GPUs were used for several deep learning applications. They have a lot of different cores and high compute. And more recently, additional IP was added to the GPUs to make them faster. So, for example, NVIDIA added some systolic array-like IP called Tensor Cores. Intel is also in the process of adding to the next generation of CPUs systolic array IP called the Advanced Matrix Extensions. The actual IP is called TIMO, which is a matrix multiplier inside of our cores. And this is going to be available in a product that Intel will release later this year in a Xeon product called Sapphire Rapids. And this will provide significant boost in performance. In addition, you have other dedicated accelerators that many different startups and some established companies are developing. And these are good for data center training and inference. Training is when you're taking a model and you're feeding it data, and initially the model is doing really poorly, but after you train it through millions of, sometimes millions of iterations, then the model converges to something that's usable. And then you deploy the model and you do what is called serving or inference. And you can do this in the data center, but a lot of inference is more recently moving to the edge. And the edge it's very interesting because you have more constraints than the data center. You are constrained by the memory, you're constrained by the power. And so often what these models that are being developed for the edge, they are smaller in memory, and on the edge you're also adding specialized accelerators so that they can you can do serving on these models in the adequate time for the end user. So a number of edge devices are adding also specialized IP for deep learning serving in particular. And in the future, in the near future, this is already popular in research, the capability to do some training in the edge is within our reach. Almost all training happens on the data center, but given in particular some of the privacy and security constraints that some end users may have, there is a desire of doing some training on the edge. So you don't have to share your data, send your data across a network and have it stored in a data center. So it's pretty exciting to see the growth of deep learning both in the data center and on the edge.
Well, let's pull it back a little bit and go back to frameworks. And so how do you see those frameworks evolving, with these new capabilities that deep learning provides? Now, we know that, the adoption of deep learning is still in its infancy. So I expect just seeing the beginning of how these AI frameworks are being used right now. But what are some of the evolutions of these frameworks that's important for technologists to understand and to explore?
Yeah, so let me just give you a high-level background of how the frameworks essentially are able to execute the data science model, the model that the data scientist creates into the hardware. So usually the data scientist writes a model, and then the model, you can think of the model at the framework level, it can be represented essentially as a graph with many different nodes and edges, and the nodes represent operations and the edges represent data dependencies. So a lot of work has been in the popular frameworks like TensorFlow and PyTorch and others, MXNet and ParoParo. These frameworks, they take the nodes and they do some fusion. So they try to cluster nodes together. And the main benefit of this is to reduce the amount of data transfers. So often you might have a compute-intensive operation followed by an operation that's very light in compute. And so you could fuse those together into one operation, and that saves the data transfer back from the compute unit to memory and back and forth to do the second operation. You can do those two operations in one. And in some cases, you might be able to fuse multiple operations. And then what happens is once you have the graph with multiple nodes, then you have a graph that is much more compacted. You can think of this as a compiled graph. And then you need to map each of those nodes in the graph to code that's going to run on the hardware. And so there are a number of libraries that are developed, particularly by both the framework teams and also the hardware vendors. So, for example, Intel has a library called 1DNN, and 1DNN takes some of the popular operations, for example, a matrix multiplication or a convolution or some other operations in the deep learning model, and it maps those to the x86 hardware to take advantage of the instructions available in both an Intel x86 and other x86 hardware. And similar with other hardware vendors, like NVIDIA has a library called QDNN that it maps these operations to the NVIDIA's GPUs. And other hardware vendors are doing similar libraries. Now, looking into the future, one of the challenges is both two challenges. One is the number of hardware that is being developed is growing. There are a number of startups that are bringing to market new hardware. So it is difficult to keep up with all the software advances for each different hardware. In other words, each different hardware would need its own library to map the operations from the frameworks to the hardware. And that work it's tremendous work. At Intel, we have a very large team of engineers dedicated to this work. And I'm sure at other companies it's the same. And so the second challenge is that the number of models are becoming much more diverse. And so having hardware vendors write libraries for specific operations that optimize specific operations is challenged because it is difficult to keep up with the pace of growth. And so in the future, what is likely to happen is that deep learning compilers are going to become more prevalent. So deep learning compilers, you can think of the regular compilers today, like LLVM or GCC, where you write code in x86, in C++, and then it maps the code from C++ to efficient x86 instructions. But it's taking several years for these compilers to evolve. And in the deep learning space, we're already seeing the birth of some deep learning compilers. They're still immature, and so it's not broadly applicable. But in a few years, to keep up with both the diverse set of workloads that are being developed and with the diverse set of hardware backends, I anticipate that deep learning compilers will become mature. There is a lot of reasons for the community to invest in deep learning compilers. And deep learning compilers essentially are going to take these operations, and without requiring an engineer to hand tune the operation to run efficiently on a hardware backend, the deep learning compiler is going to be able to quickly map a new operation to a hardware backend. And in some cases, this mapping is done using some machine learning techniques. So there are a few deep learning compilers that are being developed right now that look promising. It's still long ways to go, but it's a promising area.
I want to remind everyone that they can ask any question that they wish. We are taking questions. You can add your questions in the YouTube comments. I want to ask about those compilers a little bit in a little different context on who do you see developing training models, and who are developing these new capabilities, who are building out algorithms using training techniques that you see in AI frameworks. And I'm thinking about particular in terms of people who are familiar with the Python programming language and JavaScript developers.
Yeah, that's right. So the innovation doesn't come from one place. There is a lot of innovation that comes from some of the large companies like Google and Facebook. If you go to a AI conference, they publish a lot of papers, but it's not just one or few companies that are developing models. Models are being developed by enterprises, by smaller companies, by uh, academics, and so it's not tied to one group. The deep learning frameworks are able to democratize the development of AI models, and you often don't need to be an AI expert to develop a model. You're talking about having a lot of Python developers in the audience. These frameworks are based on Python, so people with a Python background can rapidly learn the APIs of TensorFlow or the APIs of PyTorch and develop some simple models. And as they gain more experience, then they can develop more complex models. So this is one of the great things of AI in our time. It's very democratized.
It's very democratized, and because Python and JavaScript, for instance, are well-known programming languages that are people are picking up pretty much from scratch, correct? And so then the frameworks allows them to just use the capabilities that are built into the frameworks themselves, correct?
That's correct. Yes. So they just need to learn some of the APIs that these frameworks offer, and learn some of the basics, and they can start running a deep learning model in a few hours. I've taught a number of seminars to folks that have no experience in deep learning, and within a few hours they are training and modifying a simple model, and it's very exciting to see them, and also it's very exciting for them to see the results of deep learning being applied first to simple models, but then they can grow those models and to more complex problems.
What are you excited about in your own research? One of the things I noticed in your introduction that you talk about, you even get into a little bit about the singularity, to talk about kind of the debate that's in academic circles about deep learning. What is it that excites you about what you're learning yourself as it relates to the research and the technologies that you're helping develop for Intel?
I really like how complex this problem is, that you cannot just focus on one area. You cannot just focus on building the fastest hardware without understanding the complex models that are being developed by various companies. So what I really enjoy doing is first meeting with the AI teams across various top companies, and understanding both the models that they are developing as well as the trends. What do they see in the future? And then working closely with our hardware teams to design features that are going to benefit our customers, that their customers' models in a few years. So we predict what are the customers going to need in a few years, and we design hardware features to target those needs. And in the middle, of course, it sits the software. And so working with our software teams, both the ones that are developing, that are optimizing the frameworks like TensorFlow and PyTorch, and the ones that are building the libraries like 1DNA, and also the ones that are working on advancing the deep learning compiler technology. So it's a complicated web, but it's exciting to put all the pieces together, and in addition to keep up with all the advances that are happening in the community. So there is a lot of great work from academia and from some uh, hyperscalers on AI systems, and to see the rapid innovation that is happening is pretty exciting. So keeping up with the innovation that's happening, bring that innovation into Intel, and predicting what's going to be needed in a few years from now. I find that very satisfying.
I bet. And when you go around and talk to those teams out there, and you talk about the companies and top companies in the world and their AI teams, what are the range of things that they're talking about?
Yeah, so I mentioned earlier that one of the types of workloads that drove this recent wave of AI was computer vision workloads.
Right.
But then that moved into natural language processing. And more recently, it's moved into recommendation systems. So for example, when you are choosing a product from Amazon, it's very likely that Amazon is running a recommender system behind the scenes to show you the products. Or when you are browsing as Facebook and you see a Facebook post, there is a recommender system behind that. And recommender systems, natural language processing, computer vision, this type of workloads, they are becoming very complex. So it's not just simple matrix multiplications, which was the basic component of the earlier deep learning models in 2014, 2015, but they are becoming, they have a lot more dependencies. Some of the inputs might be dynamic. Sometimes you have small inputs, sometimes large input, and the model needs to support this. So the models are getting more complex, which means if you design your hardware for one particular set, time set. So if you design hardware thinking, hey, it's 2015, the most important computation is a gem operation, and you build an accelerator that is really good at gems, then by the time your hardware hits the market 3 years later, that it's in 2018, that was no longer the case. It's becoming more diverse, and now we're in 2021. And my observation, meeting with not only from meeting with customers but also from observing academia, is that you need the capability to support both complex operations and simple operations. And if you just focus on complex operations, you might be designing the hardware that's not suitable for the future. So general purposeness becomes very important to a number of customers. Programmability becomes very important as well. And as you were mentioning earlier, the compute is 3 to 4 months. The demands of compute are doubling for deep learning training for the state-of-the-art models, and Moore's law cannot keep up with this rate of growth, and so you need to scale to multiple nodes to keep up with the rate of growth. So you need to grow both the computing in a single unit as well as the capability to scale to multiple units.
So I'm going to finish this discussion on a philosophical note. And in your introduction, you talk about the limitations of AI, and you talk about artificial general intelligence and how it's sometimes referred to as strong AI. And you describe that AGI is where machines exhibit human intelligence traits, such as consciousness and self-awareness. And, this relates back to kind of the term singularity, right? Which was coined by John von Neumann. And there's mixed opinions, you say, in the community about this concept. I'm wondering, what are your thoughts on that, the topic of singularity?
Yeah, I have a lot of respect for many people that are strong believers in that the singularity is coming. I don't necessarily see a clear path right now to singularity. So it's not something that I'm concerned. I think in the world we have much bigger problems: poverty, global warming, many other problems that I think are very important to tackle. I think the innovation in AI will continue to grow. I don't quite see, even in the academic community, like the mathematics behind consciousness are understood in order for a programmer to be able to program consciousness. It's still a bit of a mystery, and I don't yet see a path there. So it's not something that I'm concerned.
It gets into all different disciplines, doesn't it? So, Andres, I want to thank you so much for your time today. I've been joined for this interesting discussion with Andres Rodriguez. He's a senior principal engineer at Intel. We're talking about AI. You should go out and get his book. It is called Deep Learning Systems: Algorithms, Compilers, and Processors for Large-Scale Production. Andres, thank you very much for your time today.
Thank you for the invitation. It was a pleasure. I appreciate it.